So today we're going to be talking about frequency of firing, rate to summation, and rate to fatigue. I'm also going to be talking a little bit about long-term potentiation, but Josh is going to be getting into that in a couple weeks, I think, and week one. Okay, so this is a really quick concept, and so we're not going to spend a whole lot of time on the conceptual aspects of it. We're going to try to talk more about how this applies to us as functional neurologists. So the first thing we're going to talk about is frequency of firing. So this is just a very, very basic mechanism of the neuron. So the neuron's job is it receives information. If it gets enough information and the right information, then it's going to fire its axon, right? So you have a neuron here. This is my neuron, sort of. And this is, so you have all these dendrites coming into the neuron, and then you have a alright, so you have a neuron, and you have all these dendrites coming in, and they're exciting the neuron here. So once it gets to enough excitation, it's going to send an action potential, and that's going to go out, and it's going to cause this neuron to fire. So if this is a neuron that says, say a motor neuron, and the brain finally summates and it says, move your arm, it's going to move the arm. If it's for, say, the pupils, and it finally fires enough and it says, pupil, you want to dilate, then it's going to dilate the pupil. Now, like we said last week, the only neuron that we know that's monosynaptic goes from your motor cortex down to your alpha motor neurons, which causes volitional movement. So everything else, especially in the brain, is polysynaptic. So what that kind of means is here I have drawn, what, like 6 different inputs to this one neuron, but in reality, in the brain and in the cerebellum, you can have, hundreds of thousands of different connections to these neurons that cause this integration that we find in the brain. So, if this one neuron here is firing to its neighbor neuron, this might not be enough information or enough input to fire this neuron. But now say all these start firing. Now it's going to fire this neuron. And the frequency of firing is going to depend on the input. So it's kind of the very basic concept of frequency of firing. Now, the rate to summation and rate to fatigue is going to depend on the health of the neuron. So with a typical neuron, most of you guys, if you've been in cell phys, you know about the resting membrane potential. Hold on, this is a terrible color. You know about the resting membrane potential. So basically, most of this, your neurons are hovering between, let's say, -60 and -80 millivolts. And what has to happen is it's just kind of hovering here. And as you get input, it might stay there, it might go up a little bit, it might go down a little bit. But as soon as it reaches a threshold, they say approximately about -55 millivolts, you send off an action potential. And that action potential goes up, comes back down, and then it comes back to resting. So in a normal, healthy cell, this is what we like to see. It gets the input, it gets the proper amount, it fires, everything works correctly. Now, what we'll learn about a little later, I think next week actually, we talk about diastasis, which is kind of just the dying off of neurons downstream. But what happens when you're not getting enough firing to a neuron is this resting potential starts to increase. So instead of, say, this neuron being at like -80 and then having to get more stimulus to fire, it's going to be hovering around maybe -56, okay? So now, anytime any stimulus comes along, whether it's enough or not, that neuron's going to fire off. And it's going to keep firing every time the stimulus comes. Well, the reason it's doing that is so it doesn't die. It's a survival mechanism. So another thing that we'll kind of talk about is the 3 things you need to maintain a neuron. And those are activation, oxygen, and glucose. So if you're getting these 2 things, oxygen and glucose, but you're not activating the neuron, it's going to die. So the idea of rate to summation is, so this is how we're going to go practical. So say you're looking at pupils, right? Normally you look at a pupil and you shine a light in it and the pupil starts to constrict due to the light. It'll hold for a while. Eventually it'll start to get tired, it'll fatigue. You'll see it maybe hippus a little bit and then it'll let go. It'll dilate again. So what you can see with like a neuronal pool in the pupils that are starting to die out or having some issues with getting activated is as soon as you shine that light in the eye, now that pupil just constricts immediately. It just fires off right away, it's ready to go. The problem with that is because it's firing at such a high rate, it fatigues really quickly too. So a lot of times you'll see that people have TND, or transneural degeneration, in the pupillary area, mesencephalic area. Is you'll see them, you'll shine the light in their eyes, it constricts really quickly, and then dilates really quickly. Okay, so it's a really simple example of what we're looking for here. And that actually combines rate to summation and rate to fatigue, because the rate to fatigue is just how long that neuron can fire before it can't fire anymore. It's really the basics of it. So what we want to kind of do with this is apply this to every test that we're ever doing. The reason we're calling this the basics is because literally we had a seminar this weekend, and a bunch of us were talking about how it's amazing, all this cool stuff we're learning, how often we go back to just the very basics and making sure we understand that, because that's what a lot of these tests that we do and therapies come down to. So anytime you're doing a test, so let's say we already said the pupillary constriction test, how about saccades or pursuits or Rombergs? Anytime you're doing one of these tests, you want to think of what is the frequency of firing of the neurons that's causing this action, what's the rate to summation, and what's the rate to fatigue. So if I'm doing a Rombergs and I have somebody stand there and they immediately sway to the right, I'm thinking, okay, something's weird there, because normally when a person starts to sway, you know, those proprioceptors fire off, the vestibular system fires off, and it tells the body, okay, we're falling down, we need to move to the side. That should correct really, really quickly. So if it's swaying this far, the frequency of firing of the neurons that are supposed to bring me back aren't working correctly. Okay? Same thing with pursuits. You know, if you're having somebody follow your finger and you're going over here and it takes them another second until they finally look over at your finger, something's not happening correctly. So that's kind of where we want to go with the frequency of firing, rate to summation, rate to fatigue. The other thing I want to talk about, which is kind of our, I like to say like our goal in functional neurology, is long-term potentiation. So if this is your first quarter here, you may not have heard about that yet. But basically what long-term potentiation is the ability to plasticize the pathways that we're firing. So what that means is, you know, if we, we'll go back to the pupil. If we find that the pupil's not firing right, and you know, we know that it's supposed to constrict and then dilate, and it's supposed to be this nice little thing. Well, if we see that it's not firing correctly, the way to make that plasticize or have a long-term potentiation is to activate those areas and keep the neurons healthy, so that you know, you don't have to keep doing therapy every day to make these pathways work correctly. So the way that happens is, it's kind of complicated, but the very basics of it is, you have these, this is the cell. So you have these receptors. Obviously you have a ton of receptors, but you have these things called Nmda receptors. And that's not actually what they look like, but it's my rendition of it. And you have this little plug here. It's a magnesium plug. So what happens is, this is like, let's just say this is your neuron, right? So you get input from other neurons. They have their postsynaptic buttons here, right? This is where they release their neurotransmitter. And the primary excitatory neurotransmitter we know is glutamate. Okay? So this cell is being excited by another neuron, and excites it, it releases glutamate. And if you get enough glutamate, it activates these Nmda receptors. And if you get enough activation, it'll remove this magnesium plug, and it allows this channel. This is called an ionotropic receptor, as opposed to metabotropic, which has the G protein couple of receptors that have the second messenger system and everything. Anyway, this is just an ionotropic, which basically says, okay, you've excited me enough, I want to let calcium into the cell. So now you have this calcium out here, and it starts flooding into the cell. And calcium is what causes your early long-term potentiation. So when you initially fire something, like say we try a pupil and then we test something and it makes it better. So you didn't create a long-term pathway, but what you did do is create a early long-term potentiation pathway. And because what calcium does is when it comes into the cell, it has this whole cascade of events that eventually causes it to change the DNA, or not change it, but to activate the DNA to produce more proteins. And when you have more proteins, it's going to activate the cell more, allow it to fire more correctly. And if we're talking about that whole, the frequency of firing and the resting membrane potential, say it was down here at, you know, negative 56 and it was close to the threshold, now you create all these proteins, and now it's down at negative 65 for the time being. So when you do the test again now, it looks better. So this is the first way that you have the long-term potentiation start off. And then when you fire these pathways continually, it continues to rehab this cell and create this, you know, long-term potentiation and plasticity in the system, which now all these systems that you were testing that were broken are now fixed, which is really cool. And the other thing we talked about last week, I believe, was these homologous columns. And say this cell is so close to threshold that, you know, even if we fire it a little bit, it's just causing it to, you know, die or fatigue or do something that we don't want to do. Well, this is one of those situations where you can take those homologous columns and, you know, say fire a neuron over in this area. Say there's a neuron over here. Now the excitation of that, since it's homologous with this cell, is going to cause a level of excitation, but it's not going to summate it to the same degree as like direct stimulation. So this is one of those ways where, you know, I think we saw today that, or this weekend, we saw a lady that was having problems with, you know, looking over into the left. And instead of just trying to, you know, do mechanisms that made her look over into the left, they were firing it where she was looking straight forward and doing some exercises to, you know, stimulate those neuronal pools, but not specifically the ones that she was having trouble with. And as you rehab them, then she was able, by the end of the treatment, to do that, no problems, no nausea, no nothing. It's not because they were firing those pathways, it's because he was firing the homologous columns that were related to that pathway. It's kind of cool. So that's kind of the basics of long-term potentiation, but what you really, practical aspect when you go to your patients is just think, things that fire together are going to wire together. So anything that when you're adjusting somebody, if you are adding other stimulus, that's going to increase the amount of activation to those areas. And the other thing is that if you're having an area that's kind of, you know, not looking so good, it looks like it's dying, it has a, you know, fast rate to fatigue, you're going to want to start stimulating those areas with a low level of stimulus before, you know, you give them that big barrage of input. So most people, I would say 80 to 90-ish% can handle, say, like an adjustment or a bigger stimulus. But when you see those people that come in and they have, you know, MS, or they have RSD, or they have some, you know, progressed disease state, you don't want to necessarily go in and adjust them or give them this barrage of stimulus before you know the state of their neurons. So, and the way we can tell that is, you know, everything we talked about today, rate of summation, rate of fatigue, frequency of firing, stuff like that. So, for any of the new guys, I just want to kind of end now because I want to go over some questions, and I also want to do some practical stuff. So, the easiest things to do are the things that we learn in our classes, right? So the things like the saccades, the pursuits, the pupillary constriction, the Rombergs, those are things that you can do in, you know, 10 seconds and evaluate somebody a little bit better before you adjust them and try an intervention. Maybe even try eye movements, you know? So say somebody's like, you see a Rombergs and they're swaying all over the place, you know, maybe you don't want to blow them up, you know, with an adjustment right away. Maybe you want to give them some eye movements to try to facilitate the canals or the vestibular system that's having this aberrancy. So let's start off with, I'm going to try pursuits, saccades, and pupillary constrictors. And I want you to do all three of those tests on one person and then switch and see what you find, do some sort of intervention. And you can ask some of the older guys for interventions, whether it's eye movements or, you know, passive range of motion, whatever. And we'll see if we make any changes. So next week, I think we're going to be going over diastasis. And so stick around for that. All right. Thanks, guys.